Welcome everybody to Algebra 2, Section 2.1, Relations and Functions. So let's first talk about relations, and it's a set of ordered pairs that can be shown in a table, mapping, or sometimes called a mapping diagram, a graph, or expressed as an equation. The set of x values is called the domain, and the set of y values is called the range. A relation with distinct points is called discrete, and if those points are connected and it has connected lines or curves, it's then called continuous. So let's go more specific. More specific than a relation is a function. So all functions are relations, but not all relations are functions. Excuse me, one way but not the other. So a relation is which, let me try that again. A function is a relation in which each element of the domain is paired with exactly one element of the range, aka each element of the domain, that's each x. So each x is paired with exactly one element of the range. So one element of the range is the y's. So each x is paired with one y is the idea we're getting at. So for example here, if we have this set of ordered pairs, this relation, so the first ordered pair I'll write is 0, 1. Put a comma and write the next ordered pair, -5, 2, comma, and do the next ordered pair, 6, -2, 5, 7, and 3, 7. This is a function because as we look at each of these x's, each x only goes to one y. By goes to means paired with. So 0 goes to 1, -5 goes to 2, 6 goes to -2, 5 goes to 7, and 3 goes to 7. So every x goes to only one y. Now you might notice here at the end, both 5 and 3 go to 7. That's okay, and that's still a function because they're different x's going to the same y, and we're only concerned that each x goes to only one y. It would be an issue if there were two x's, if there was one x going to two different y's, not two x's going to one y. So not a function here. Here's a non-example. -7, 2. 6, -1, 6, 3, -3, 9, and 4, 0. And what causes the issue here is that we have 6 repeating there. It goes to both -1 and 3, and that means it is not a function. A good way to think about it is a vending machine. So for example, a function would be how a vending machine works. You put something in, the x value, and you get something out. So let's say for 0, I push E5, and that's 0, and then I get a Pop-Tart out. I push whatever button -5 would be on the vending machine, and I get a Twix bar. I push 6 on the vending machine, and over here it pops out a Snickers, and so on and so forth. And so here at the end, we notice both 5 and 3, we push the button for 5, and we notice, oh, Skittles pops out. We push 3, and Skittles pops out again. And that's how vending machines work. There are multiple slots for the most popular items. Whereas over here for the not a function part, that would be like a broken vending machine, in which I can push one button, 6, as my input. I push that button 6, and maybe one time I push it, and I get a Twix. But the other time I push it, I get an Almond Joy. And that would suck because Almond Joys are terrible. So you want to make sure that when you plug something in or when you put an X in, that you only get one specific Y out, rather than potentially two different ones, and you have to figure out which one would it be this time. I don't want to risk getting an Almond Joy. Those things are just terrible. So vertical line test. If we have a graph function, such as this right here, if a vertical line passes through more than one point, then it is not a function. So if I just draw a bunch of vertical lines going through here, we notice that every vertical line hits 1 point or less than a point. Over here, it would always hit a point, but our concern is if it hits more than 1 point. So we're not concerned if it were to somehow hit none, we're only concerned if it hits more than one. And so there's no area on the graph, no vertical line that I could draw that would ever hit more than 1 point. So thus, it is a function. Now over here, the not a function, if I draw a vertical line here, for example, it hits 2 different points on the graph, making it not a function. So even though there's spots where it hits none, and there's spots where it hits only 1 point, those aren't the concern. The concern is that there's at least one place on this graph that a vertical line would cross the graph twice. And because there's at least one place where that happens, it is not a function. So now we're going to find the domain and range of these relations, and then determine if the relation is a function or not, based upon whether those x's repeat or each x goes to exactly one y. So the domain, what we do is we use a capital D for domain, and as we defined it earlier, it's a set of x values for the relation. And so I'm going to put this brace at the beginning, just telling us it's a set or collection of numbers, just like this is a set or collection of points. And I'm going to list all the x values. Now, I am going to be a stickler about this, that it's not just listing the x values, but it's listing the x values exactly once from least to greatest. Once again, exactly once from least to greatest. That might be something you want to take note of. So -1 is our lowest x value, 0 is the next, followed by 4, and followed by 6. So they were already in least to greatest order by the x values here. And then I'll put the brace at the end, telling us that set or collection of numbers is done. Now as I do the range, once again, it's an R for range, not once again, but just similar to how the D is domain, the R is range. Notice the double line is real numbers, but that single line R is the range. And I'm going to put that brace for the collection, and Y values will do the same exact thing as X values, where we do them least to greatest, but no repeating. You only write each value one time. So -9 is the smallest, followed by -5, followed by -2, and last but not least, we have 3. So the y's went out of order compared to how they were written originally. And then is this the function, aka, do any of these x's go to multiple y's? And if no x's repeat, then yes, it is a function. Number 2 here, the domain. The smallest number is -3 for the x values, then comes 5. And even though there's another 5, there's 2 of them, we only write it one time for our domain. And then we put 8. We're just saying these are the x values that appear. We're not concerned with how many times they appear when we're listing our domain. For the range, the y values that appear from least to greatest would be -6, 0, 2, and 4. And then when we ask whether or not this is a function, we consider, well, did an x repeat? And sure enough, 5 repeated. 5 goes to both 2 and -6. That'd be like our broken vending machine where I don't know if I'm getting a Twix or an Almond Joy, and I do not want to risk getting an Almond Joy because those belong in the garbage. Number 3 here, it's the same idea, but now it's listed in a table this time, okay? So this was the collection of points, the array of points, and this is a table where 7, -8 would be an ordered pair, 2, 3 would be another ordered pair, and so on and so forth down the table. So doing the domain, least to greatest would be -4, 0, 2, and 4. The range, least to greatest, would be -8, -1, 3. So because those 3's repeat, you only write it one time. And what is this a function? So even though the y's repeat, that's okay. That just means that multiple spots in the vending machine have the same item. Must be a popular item. So I'd be like I pushed two different buttons, and either button could get me Skittles. So yes, it is a function. We are not concerned with the y's repeating. We're only concerned with the x's repeating. On this next one here, domain would be from least to greatest 10, 15, 18, 24. And the y's from least to greatest, the range would be 0, 3, 7, and 11. And as no x's repeat, this is in fact a function. Going to the next page, we have a couple more examples. These are mapping diagrams. Mapping diagrams to start with on 5 and 6. And what this is you put the domain on the left, the range on the right, and as such, being domain and range, we do list them least to greatest. As you can see there, the x's are least to greatest, and so are the y's. And you do not repeat. So how you know what goes to what is through these arrows. -4, 0 is an ordered pair. -2, 3 is an ordered pair. And notice how 5 has 2 arrows. So 5, 7 is one ordered pair, and 5, 9 is a second ordered pair. So the domain is already listed for us. We just repeat those numbers in the exact order they're in currently because it should already be least to greatest. And no repeating. The range would follow the y's as well, least to greatest, no repeating, which is what's already listed in the mapping diagram. And then whether or not it's a function. So 5 goes to both 7 and 9. That's that broken vending machine. The x's repeat, so no, it is not a function. On number 6 here, the domain, the x values least to greatest would be 2, 8, 13, and 17. The range, least to greatest, would be -4, 0, and 7. And yes, we have 2 arrows going to 7, but we only write the 7 once, even though it's part of 2 ordered pairs, 2, 7, and 17, 7. And even though that repeats, it's not an x repeating, and so yes, it is a function. Number 7, we have this collection of 5 points. So the domain would be finding the x values in all these points. So the x value of those points are both -3, so we write that one time. This point, the x value is 0. This point, the x value is 2. And our last point, the x value is 4. The range, we look at the y values, and we go least to greatest, which would be low to high. So the lowest one would be -5. The next one would be over here at -2 for the y values. The next one for the y value, oh, my pencil glitched out there for some reason. The next one up here would be -1. Here is +1 for the y value. And last but not least is the 4 for the y value. Now, is this a function? No, because these both share the same x value. Or if you do a vertical line, you hit more than one point. So, no, it is not a function. On number 8, the domain here, we don't see a set of points like we have on the first 7 problems. Instead, we see a line telling us it's going forever left and forever right. So as we do the domain, we know it goes to both -infinity and +infinity. And so you can say that it's all real numbers. You could write out all real numbers. Or you could do that double-lined R for the real number system, saying anything that's a real number works. Because it goes forever left, forever right, and everywhere in between. As far as the range goes, we want to say how far low or how far down, how far up it goes. Well, this arrow dot only tells us it goes left forever, but it goes down forever. And up here, this arrow dot only tells us it goes right forever, but up forever. Meaning this is also all real numbers, which you can also express by doing the double-lined R. And yes, it's a function because there's no place that I could draw a vertical line that would ever intersect more than one time on the graph. So yes, it is a function. Number 9 here, the domain. Well, this does not go forever left. The farthest left it goes is right here. It does go forever right, here and here. This would go slowly to the right, and this goes a lot quicker to the right. But it does go forever right. And so the collection of numbers is starting at -4 and everything bigger than that. So it'd be x is greater than or equal to -4. Because once again, it's -4 and everything bigger. The range, this arrow means it goes down forever, and this one it goes up forever, and it's everywhere in between as far as the y values. There's not a spot where it's just like doesn't exist or anything like that. And so it would be the real numbers. So that double-lined R are all real numbers. Now, is this a function? Well, I could draw a vertical line right here that would hit more than 1 point. So no, it is not a function. On number 10, it's everywhere for the left and right. The domain is left and right, the x values. It's from this on the left to over here on the right. It's again here on the left and here on the right to make it incredibly aggressive. So the farthest left it goes is this point right here, which is -2. The farthest right it goes is over here, which is 5. And it exists everywhere in between. So we're going to do this compound inequality that x is greater than or equal to -2, while also being less than or equal to 5, aka everything between -2 and 5 is fair game. The range, how far low and high, we'd say, well, it goes lowest down here when y is -2, it goes highest up here at y equals 4, and it exists everywhere in between. So it'd be -2 is less than or equal to y. That's a change because we're putting y here because it's the y values, not x, is less than or equal to 4. And is this a function? No, because there's multiple vertical lines that would hit more than 1 point, and we only need one vertical line for it to not be a function that hits multiple points. Let's go ahead and look at number 11 here. Y equals -x squared plus 3. So in order to do this one, we're going to have to utilize our graphing calculators. So I'm going to go over here to my Calc84 graphing calculator, which operates very similarly to our TI-84s that we have in class here. And so I'm going to go to y equals up here at the top middle, and it turned my plots on. Oh, I don't want that. Let me try again. There we go. I must have hit second in y equals on accident and gone to the stat plot option. And I type in my function. It already has the y equals part off to the left, and so I just write in after that. It's -x. The x is right underneath the mode button, the one with xt, the 0 with a line across called theta, and the letter n. So the x button, then I do the exponent of 2 plus 3, and I graph this one so that way I can see what's going on. And as I see what's going on here, I can zoom in, I can zoom out, all this stuff, and I notice that as I move throughout the graph, it looks like it's going forever left and down, as well as forever right and down. So to my domain appears to be every single number, all the real numbers. So I'm going to put real numbers, or all real numbers. The range, or the y values, let's look at the graph again here. This tops out at the top of this a red hill there, so to speak. It's called a parabola, and it goes down forever. So it's this spot up here, which as I zoom, I can see the top is 3 there. And so as I look at that, I say, oh, okay, the highest it ever gets is 3. There we go, now we can see that a little bit better. The highest it ever gets is 3, and so because the highest it ever gets is 3, but it goes down forever, we're going to write it as an inequality. Similar to what we did on number 9 for the x values. So for range, y is less than or equal to 3 because it hits a y value of 3 and everywhere lower than that. But the maximum y value it got to is 3. And was that one a function? Yes, it was, because no vertical line would have ever hit more than 1 point on the graph. Let's turn our attention to number 12. Once again, we'll be using our graphing calculator for this one. I believe you guys have Calc84 on your iPads as well. You can also use Desmos as a web app, or they have an app on smartphones as well, and tablets that you can use. That can be a helpful one. So -5x minus 1, go to graph, look at this graph, And I'm going to zoom way out so I can see what's going on here. And it goes forever up and to the left, forever down and to the right. So since it goes forever left and right, the domain is all real numbers. And it goes forever up and down, which is all real numbers again. So it never maxes out on the top, or maxes out on the bottom, or maxes out on the right, or maxes out on the left. And was it a function? Would any vertical line have ever crossed that, or crossed more than one point on the graph? No, no vertical line would have crossed more than one point on the graph. So yes, it is a function. Number 13, y equals -7. So y equals -7, pulling up Calc 84 again, and going to my graph again, or my y equals menu, to type this in. I just type in -7 because it already has the y equals for me. I go to graph, and it's just a horizontal line at the y value of 7. -7, I should say, because it says y equals -7. So no matter where you look on the graph, however far out you go, as we go to the thousands on the y-axis, you can see there, the x value is always -7 regardless, because y is consistently 7, or -7, I should say. So the domain, how far left and right it goes, is every single number. Let me close that down so you can see it better. All real numbers. Whereas the range is only ever y equals -7. It never changes. So domain, the double line R for all real numbers. The range, y equals -7. It's never anything else. And then is this a function? Yeah, because no vertical line would have ever crossed more than one spot on that graph. Now x equals, on this problem number 14, we can't type x equals into this graphing calculator. You can actually on Desmo's graphing calculator, but we can't type it on these TI-84s or Calc 84s. Now, as we noticed, y equals -7 was a horizontal line where y is always -7. So if I just sketch a little graph here quickly, x equals -1. Well, that's true right here at -1. And so we'd have a point there. X is also -1 up here, because it's still -1 or 1 to the left. It's true here at this point, this point, this point, this point, this point, and this point. No matter how high up and down I go, I'm still 1 to the left of the center. So it's still the x value being -1. So x equals a number is a vertical line at that value, at that x value, I should say. So the domain, how far left and right it goes, it only ever equals -1. Whereas for y values, how high up and down it goes forever up and down, which is all real numbers, because every single number you could ever think of would be included. And is this the function? Well, this vertical line hits every single point. That's definitely more than one point. So no, it is not a function. It fails that vertical line test, as we call it. Now we're going to move to the next page and talk about function notation. So function notation, equations that represent functions are often written in function notation. So notation is just a way to write things, and this is a way to write functions. So for example, we have the equation y equals 2x plus 7. This can be rewritten as f of x equals 2x plus 7. So the only change is that y is replaced with f of x. And similar to how typically for functions or for equations, we plug in an x value and we get a y value out. And similar in functions, we will plug in an x value and we get a y value out. And what this is saying is it's a function on the variable x, a function involving the variable x, or involving the plugging in of the variable x. So here x is the input and f of x, which is the same as y, is the output. Now you might be wondering, if f of x is the same as y, what is the reason for having function notation? Why don't we just keep it as y? Why bother changing? And there are three primary reasons that function notation is helpful. One, we automatically know it's a function when it's written this way. We just did on all of those problems previously where we had to determine whether or not something was a function. Whereas if it's written this way with f of x, we instantly know it's already a function. So that's one reason, is it allows us to know already whether something's a function or not. The other reasons we'll see in just a moment. Function notation is specifically useful for finding a value in the range that corresponds to a certain domain value, aka finding a y value that corresponds to a certain x value. So if f of x equals 2x plus 7, find f of negative 3. What this is saying is we want to know what comes out of the function, what the y value would be, when x is negative 3, when we plug negative 3 in. So what happens is we rewrite this left side as f of negative 3. Then on the right side, everything stays the same except for we replace or substitute x with negative 3. And so because x is multiplying with 2, negative 3 will do the same. So now we continue writing. We have f of negative 3 on the left-hand side. That's going to stay the same throughout in every single step. We will not be changing what's on that side. On the right side, we do order of operations. 2 times negative 3 is negative 6, and we'd add 7 to that to get 13. And once again, that left side is not changing. It stays f of negative 3. And we consider this to be finished, meaning if you were to plug in negative 3 into this function, you would get 13 out. And now I can show the second reason why function notation is useful. By looking at this final line, we can already know a lot of information. We know 3 pieces of key information. We know that we plugged in negative 3. We know we plugged it into this function f, and we know we got 13 out. So we know what we plugged in, where we plugged it into, and what we got out, just from looking at that last line. Whereas if you were to just have called this y equals 2x plus 7, we would not necessarily know instantly by the end of this. You would have y equals 13 if you plugged in negative 3 for x. You wouldn't know by looking at this line what you plugged in. Where here, you know exactly what was plugged in. And we also don't know that it's a function as we talked about earlier. And the third reason why function notation is helpful comes into play on this next group of problems, 1 through 6, where we have 2 different functions listed here. We have an f of x and a g of x. And using a new letter outside, f, and then a new letter g, helps to distinguish or separate the fact that these are 2 separate functions. And so when we have problems that say f of a number, we plug it into f of x. Whereas when we have problems that say g of a number, we plug it into g of x. And so the third reason we like function notation is it helps us to distinguish different functions more easily. So here on number 1, f of negative 9, and we're told f of x is this, so we'll plug it in there. And we have negative 5 times negative 9 minus 14. My iPad just zoomed on me for some reason. Then we're going to have f of negative 9 equals, as we do the order of operations, we get 45 minus 14, which results in f of 9 equaling 31. And I do want your answers written like that, where you have that f of negative 9 is equal to the number. Because as I mentioned, that's one of the reasons we like function notation, is because we can instantly see what was plugged in, where it plugged into, and what came out. Now, you might be wondering, in these, do I have to write f of negative 9 every single time on the left-hand side? And the answer is that if you write it on the first step, like we have it already up here, if you write it on the first step and the last step, and you keep your equal sign in approximately the same location, left and right, so you don't just move it all the way over here for some reason, then you don't necessarily have to write it in the middle steps for f of negative 9. You could still choose to write it, and that's perfectly okay, or you can choose to leave it. I personally choose to not write it on every single step in the middle because that's a lot of writing. Now the reason you can ignore the ones in the middle is because if we have the one at the top and the bottom, we know all the ones in between that are sandwiched there in between the top and bottom are part of the same function and the number we're plugging in. So on number 3, f of 3 over 10. We'll plug that into f of x and get negative 5 times 3 over 10. minus 14. So as I look to multiply negative 5 times 3 over 10, I'm going to put negative 5 over 1 and cross reduce. 5 goes into negative 5, it becomes negative 1. 5 goes into 10, it becomes 2. And as we multiply straight across, I end up getting negative 3 over 2 minus 14. In order to combine these, I will need to get common denominators. 14 is currently over 1. Multiply this by 2 over 2, and this becomes 28 over 2. Feel free to do that work more off to the side than I did there, but I went ahead and just did it in line with this problem here because I can quickly change it. So now I can combine negative 3 and a negative 28 to get negative 31 over 2. The bottom stays the same. And now f of 3 over 10 is equal to negative 31 over 2, or negative 15.5, or negative 15.5. They all are the same thing, just different ways of writing or representing that number. And so notice I didn't write my f of 3 over 10 on the middle step, but I wrote it again on my final step. Number 3, we have g of 0.4. So that means we're plugging it into this function here. So g of 0.4 is negative 0.4 squared. Notice I'm putting it in parentheses when I square it. That's important. 9 times 0.4 minus 1. Now as I do 0.4 squared, I end up getting 0.16. And it's a negative 0.16. The negative is outside the parentheses. It is not part of what's being squared. So we don't do a negative times a negative. It's a positive times a positive, and then we make it negative. 9 times 0.4 is 3.6, and we subtract 1. If we combine these three numbers, we end up getting 2.44. And since I'm now at the end, I rewrite that left-hand side, g of 0.4. I want to clarify that number 0.4 on the left side and the number on the left side every single time is not anything that we need to add, subtract, multiply, or divide with. It is just telling us, hey, here is what was plugged in. That way we can see it again at the end, and at any step in between we choose to write it on. Number 4, g of negative 7. So we're going to have negative of negative 7 squared. Two negatives there, one from the negative 7, one from the negative x squared. But the one with the negative 7 is part of the parenthesis. Plus 9 times negative 7 minus 1. So here, negative 7 squared is a negative times a negative. That's a positive 49. However, this negative out in front remains, and so it's negative 49. 9 times negative 7 is negative 63 minus 1. If we combine all of those, we get negative 113. So g of negative 7 equals negative 113. On to number 5. This is odd. We have f of 1 minus f of negative 4. So essentially what we do is we figure out what f of 1 results in, we figure out what f of negative 4 results in, and we subtract the two results. So a good way to go about these problems is to do the work for each of these separately, off to the side somewhere. So I'm going to do f of 1 right here, for example. So I plug in 1 into f of x, and I get negative 5 times 1 minus 14. Then I end up doing my order of operations like I have been, and getting negative 5 minus 14, which results in f of 1 equaling negative 19. Now I will go ahead and find f of negative 4. So as I find f of negative 4, it is negative 5 times negative 4 minus 14. And then I will multiply negative 5 times negative 4 and get 20 minus 14. And now f of negative 4 results in 6. And so now I do f of 1 minus f of 4. F of 1 is 19. And f of negative 4 is 6. And I get the result of 13. Meaning f of 1 minus f of negative 4 is 13. And I write my answer as so, including the f of 1 minus f of negative 4. That way, once again, it can be followed along saying, wait, how did you get 13? What did you do? Well, part of your answer is that, hey, here's what we did. We plugged 1 into f, we plugged -4 into f, and we subtracted the 2. So I just went ahead and utilized the fact that it was already written up here to not write it again. But if you wanted to write it again, you're more than welcome to. You would just write f of 1 minus f of -4 equals, 13. I almost wrote -13, but 13. And we could just write our answer down here all the same. Number 6, 2 times g of 12. So what this means is, just like anytime we have grouping symbols, we go inside out, we're beginning. So I'm going to plug 12 into g, and whatever I get after that, I will multiply by 2. Now, you can go ahead and either do g of 12 off to the side and then double it at the end, or a way I like to write it personally is I'm going to plug 12 into g and get -12 squared with the negative outside the parentheses there, plus 9 times 12 minus 1, and I'm going to put the whole thing in that bracket with 2 multiplying it. So inside is g of 12, outside is this 2. And I'm going to go ahead and just continue to do this math. Once again, if you wanted to do g of 12 off to the side and then multiply the result by 2, that is perfectly fine as well. So I'm going to rewrite that 2 because I'm not doing anything with it yet. 12 squared is 144, and then we make it negative. 9 times 12 is 108, and that is positive, and then we subtract 1. Inside that bracket, we end up getting the resulting number as -37 when we combine those three numbers. And now, as I do 2 times -37, I get -74. So 2 times g of 12 is -74. And I write my result once again just like that with the left side looking as I wrote it there. Now we're going to move on where we're using p of x and q of x. Once again, just different letters showing that they're different functions. And these involve some fractions and absolute value. How exciting. So p of 9 over 16, we plug that into p of x and get 1/2 minus 4/3 times 9 over 16. So I have this multiplication here, so I'm going to look to cross reduce. 4 and 16 reduce to 1 and 4. 3 and 9 reduce to 1 and 3. And now I have 1/2 minus 3 over 4. In order to actually combine these, I need common denominators. My common denominator will be 4, so I multiply the top and bottom of my 1/2 by 2, and I get 2 over 4. If I actually combine those now, it results in -1 over 4 as we do 2 minus 3 on the top, and keep the bottom the same. So p of -9 over 16 equals -1/4. On number 8, q of 5, I'm going to plug that into my x. And now you might be wondering, which x do we plug it into? The answer is both. So I wrote 8 for a second there, thinking about this. 3 of 5, 3 times 5, minus 5 cubed. So 3 times 5 is 15, and 5 cubed is 125. That'd be the absolute value of -110. Reminder, you don't use the absolute value to make it positive until you do everything inside. So this becomes positive 110. So q of 5 is 110. Let me try that again. There we go. A less bad box. Number 9, q of -2. So that would be the absolute value of 3 times -2 minus -2 being cubed. So 2 negatives in a row there. That's -6. This becomes -8. But this minus sign is still there. And so when you have 2 negatives in a row, we're really adding. I like to say instead of bussin', we're plussin'. And now we combine those and we get 2. So the absolute value of 2, which just is 2. So q of -2 is 2. Number 10, p of 18. So that would be 1/2 minus 4/3 times 18. I'm going to put that 18 over 1 to make my life easier as I multiply these fractions. As I look to cross-reduce here, I say 3 and 18 become 1 and 6. And so I have 1/2 minus 24, or 24 over 1. And I am going to put it over 1 because I need common denominators. So I'm going to multiply the bottom by 2, which means I need to multiply the top by 2, making it 48. As we combine the tops, 1 minus 48 is negative 47, and you keep the bottom the same over 2. So as a mixed number, that would be negative 23.5, or a fraction negative 23.5, and p of 18 is equal to this. Whether it's an improper fraction, mixed number, or decimal, I do not care. Let's do another page worth of examples here. On number 11 and 12, we're using the exact same p of x's as we did before and q of x. So as we do 7 minus q of 4 minus 4.5, we can do q of 4.5 out to the side if we want, and then take 7 minus the result. Or we can do it as I did the 2 of g of 12 earlier, where I do 7 minus, and then after that minus, I'm going to have my q of x, reminding us that q of x was the absolute value of 3 times the x value, in this case 4.5, minus 4.5 being cubed. Now, if this wasn't already in a grouping symbol, such as absolute value, we would have to put it in parentheses because we're subtracting the entire result, meaning we have to do all that first and then subtract. 7 minus, working inside out, 3 times 4.5 is 13.5, and 4.5 cubed is 91.125. It is important that you don't want to round until you get to the end if you can help it. So we'd like to keep it there at 1.125 rather than rounding it to 0.1. So 7 minus the absolute value of these, as they subtract, it becomes negative 77.625. That is 7 minus 77.625 because this becomes positive, but the other negative outside remains. And as we combine these, we end up getting negative 70.625 as a result. So 7 minus q of 4.5 equals that number. And if it here it doesn't specify it around, but let's say I did specify it around your answers to the nearest tenth, we would just say, hey, this 2 tells us it rounds down, and it's 70.6. Number 13, or excuse me, number 12 here, my apologies. I saw the 3 and it conflated my mind. So 3 of p of negative 1, or 3 times p of negative 1, plus 5. So I take p of negative 1, I plug it in, and I find that result. I multiply by 3 and subtract 5. So I could do all those as separate steps, like find p of negative 1, and then do that other math from there where I multiply by 3 and add 5. Or I can do it how I'm about to do, where I have 3 bracket p of negative 1, which would be 1/2 minus 4/3 times negative 1, and then add the 5 at the end from over here. And since this was not in grouping symbols originally, I had to put it in some sort of grouping symbol now, since it's being multiplied by 5 and or multiplied by 3 and added by 5. So negative times a negative creates a positive, so it becomes positive 4/3 as we multiply by negative 1. Then I need common denominators in order to actually add these, and so my common denominator is going to be 6. So I multiply by 3 in this fraction, and I get 3 over 6. I multiply 2 in my other fraction over here, and I get 8 over 6. And as I add these on the numerator, I get 11, and I keep the denominator the same, 11 over 6, and then plus 5 at the end. Now I multiply 3 with the 11 over 6, and I can cross-reduce. 3 becomes 1, and 6 becomes 2, and so I get 11 over 2 plus 5. And similarly, we'll need to put 5 over 1 to get common denominators yet again. My common denominator would be 2, so I multiply 1 by 2 and get 2. I multiply 5 by 2 and get 10. And now as I combine these, I end up getting 21 over 2, which is 10.5 or 10.5. So 3 of p of negative 1 plus 5 is 21 over 2, or 10.5. Now on numbers 13 and 14, these are a different type of problem entirely, actually, believe it or not. Notice here we have f of x equaling a number instead of f of 34. Very different setup. And what this means is we're saying, as if, remember, f of x is y equals 34. Find x. We're saying we got 34 out. What did we put in? I got a Twix from the vending machine. What button did I push? Becomes the question. And just like sometimes there's multiple buttons, it's possible there could be multiple answers depending on if it's an absolute value problem, for example. So I use f of x equals this as my base. And so reminder, if this was y and this was y equals 34, what would happen is we would just replace y with 34 and set it equal to 3x plus 19. So we'll do that exact same thing here. I'll showcase that real quick. It would have been 34 equals 3x plus 19. And that's exactly what happens here. We take f of x equals 3x plus 19 and just swap out f of x for 34 since we're told they're equivalent. And so now that we have 34 equals 3x plus 19, we're going to go ahead and start solving this for x. So we're not doing order of operations here. Here we're undoing the equation to get x by itself. So we subtract 19 from both sides and get 15 equals 3x. Divide by 3 and we get x equals 5. Meaning 5 was plugged in order to get 34 out. Similarly, on number 14, if f of x equals negative 62, we're told that's what came out. What went in, find x. So I take my f of x, and I replace f of x with negative 62, and I write the remainder of that function, 3x plus 19. And now I start solving here. I would do that by subtracting 19 and getting negative 81 equals 3x. Dividing both sides by 3 yields x equals negative 27. On number 15 here, Owen paid a landscaping company $108 for an initial lawn treatment, then $70 per month thereafter. The function p of t equals 108 plus 74t represents the total amount of money he will have paid after t months. So we're saying t is the amount of time in months, 108 for the initial treatment, 74 per month or every single month, so it multiplies per the number of months, and we add that up to how much he's paying, or p, the y value, what we get out over that time frame. So find p of 24. So p of 24, we plug that in, 108 plus 74 times 24. That'd be the equivalent of 2 years, 24 months. So that's 108 plus 1776, a little patriotic there. 108 plus 1776 is 1,884. So P of 24 is that. Now it asks specifically, what does this represent? So it represents that Owen paid $1,884 after 24 months, aka 2 years. Now, we're wondering, how long has Owen been receiving lawn service if he paid a total of $2,994 to date? So this is the Y value, or the P that came out, that he's paid. We're wondering, what's the T in months? So similar to what we did on problems 13 to 14 up above, we're going to replace the P of T with 2,994 and set it equal to the other side of the function, 108 plus 74t. And now we start solving this equation for t by subtracting 108 and getting 2,886 equals 74t. If we divide both sides by 74, we get t equaling 39. We need a label, so it's 39 months. If you have labels, you use labels. Our last part of the problem, or part of today, I should say, we have f of x and g of x reassigned as new functions compared to what they were earlier today. And we notice as we're plugging these in, these aren't normal. That's not just a number, it's an algebraic expression involving numbers and variables. Now, you still plug things in the exact same way. So f of c plus 2, we replace x with c plus 2. So negative 4, parentheses, c plus 2 plus 9. Now, how we go about the math will change. We still multiply, but here we're distributing, and we get negative 4c minus 8 plus 9. Now, as we look, we say, well, we can only combine like terms. I can't combine negative 4c with anything, so I rewrite it. But negative 8 plus 9 give me positive 1. And that's as much math as I can do. And so f of c plus 2 is negative 4c plus 1, aka I plugged c plus 2 in to the function f, and I got out negative 4c plus 1. Number 17, we're supposed to plug in 7w minus 5 into f of x. So that would be negative 4 times 7w minus 5. Add that to 9. So that would be negative 28w plus 20 plus 9. Combine like terms to get negative 28w plus 29. So we plugged in 7w minus 5 into the function x, or f, excuse me, and we got out negative 28w plus 29. On 18, plugging negative 4y cubed into g of x. So this would be negative 4y cubed being squared, because the x is squared, minus 5. Now if we do 4y cubed times, or negative 4y cubed times negative 4y cubed, that's what that means. 2 of these. Negative 4 times negative 4 is 16, and y cubed times y cubed, when you multiply the same base, y, you add the exponents, and we get y to the 6th. So we don't change the exponents when we add and subtract, but we do change the exponents when we multiply and divide. So this ends up becoming 16y to the 6th minus 5, and that cannot be combined, so we get g of negative 4y cubed equals 16y to the 6th minus 5. I want to note that if you don't want to write out this twice, you can multiply this exponent to each exponent inside, but be careful. 2 times 3 is 6, but there's an exponent on the negative 4 as well, of a 1. And so that becomes negative 4 squared, with negative 4 being in parentheses, y to the 6. Multiplied to each exponent inside. And negative 4 squared, as we mentioned, is 16, and that becomes 16y to the 6th. Number 19 here, we're plugging a minus 3 into g of x, and that would be a minus 3 quantity squared minus 5. Now, we can't do that little trick where we multiply this exponent to each exponent inside on this problem, because there's addition and subtraction inside. That only works when the whole parenthesis or the whole quantity is multiplying or dividing, or some combination of the two. But anytime there's addition and subtraction, we can no longer do that. So the common mistake is we call this a squared minus 9, but that would be wrong. And it would also be wrong to call it a squared plus 9 as well. What I encourage you to do is to do this work off the side where we actually write both out. And then we might remember we have to do what we call foiling, where we distribute everything in the first to everything in the second. So one by one, I'm going to do a times a and get a squared. A times negative 3 and get negative 3a. Negative 3 times a and get negative 3a again, and negative 3 times negative 3 and get positive 9. So as I combine like terms, I get a squared minus 6a plus 9. So if we try doing that little shortcut we did earlier, which is incorrect, we miss out on this minus 6a. That is a part of the problem. So we get a squared minus 6a plus 9 minus 5. And now we combine like terms here to get a squared minus 6a plus 4. And that's all we could do. We can't combine anything else, so g of a minus 3 is equal to a squared minus 6a plus 4. So we got out when we plugged in a minus 3. So on number 20, oh boy, g of 2m plus 1 minus f of 3m minus 7. So I encourage you to do these as separate problems. If you wanted, you could do it as one big problem where you just put a bracket around your g and your bracket around the f and you subtract the 2 in the middle. But I encourage you to do these as separate problems. That's how I handle them personally. But once again, you're free to do it the other way if you'd like. So g of 2m plus 1 would be 2m plus 1 quantity squared minus 5. Once again, because there's addition or subtraction in the parentheses, we can't just do this trick. That would not work here. We instead want to write it out twice. Now I will note that as we write it out twice, there's also a shortcut that I'll show afterwards. So if I do 2m plus 1 times 2m plus 1, I end up getting down here 4m squared, 2m plus 1, which results in 4m squared plus 4m plus 1. So I'll write that back up here. We have the minus 5 still. Now the shortcut that does work for this is you square the first part, 4m squared. You square the last part, 1. And in the middle, you multiply these together. 2m times 1 is 2m, and you double that and get 4m. And it is positive because these were both positive, because 2m times 1 is a positive 2m. I'll showcase that on the last one too. It would have worked here. A minus 3 quantity squared. A squared is a squared. You square negative 3 and you get positive 9. We multiply these together and we get negative 3a. Double that, we get negative 6a. So that's a shortcut you can do as well, where you square the first, square the last, and in the middle, you multiply those two together and double it. Down here, let's finish off g of 2m plus 1 by getting 4m squared plus 4m minus 4. Now we have to find f of 3m minus 7. So f of 3m minus 7 would be negative 4 times that parentheses, 3m minus 7, plus 9. So now we look to simplify, or distribute it, I should say. Negative 12m plus 28 plus 9, which results in negative 12m plus 37. So f of 3m minus 7. So now all of this, we subtract those two results. So we do this minus that over there. So I'm going to do that off to the side as well. And as I do my g part, the g function, that's 4m squared plus 4m minus 4. And then as I subtract, I need to put the second one in parentheses because we're subtracting the whole thing, negative 12m plus 37. The reason why it's important to put that in parentheses is because now as I change this to an addition and I change every sign in the following to the opposite, I get the correct signs. That's a positive 12m, that's a negative 37. And now I look to combine these two. So 4m squared combines with nothing else. 4m combines with 12m to create 16m. And negative 4 combines with negative 37 to create negative 31. All that to say, g of 2m plus 1 minus f of 3m minus 7 equaled all of that as our answer, which you also just could have rewritten up here. I'll use a different color. You could rewrite this up here and box this as your answer as well. And that is it for section